On behalf of the organizing committee, it gives me immense pleasure to welcome all the participants to the second talk of day 4. This talk will be delivered by one of my colleague, Dr. Naresh Kumar. He is working as an assistant professor in the Department of Mathematics and Computing, Dr. B.R. Ambedkar National Institute of Technology, Jalandhar, Punjab, India. Dr. Naresh Kumar uh, has research interests include numerical methods for partial differential equations and high performance computing for finite element methods with polygonal meshes. His PhD dissertation was in the weak Galerkin finite element method for time-dependent problems on polygonal meshes. Dr. Naresh Kumar has delivered lectures in various workshops and conferences, and he has published several good research papers for his credit. He has vast knowledge on finite element method and its implementation for solving elliptic boundary value problems. Today, he is going to deliver the talk on the topic weak Galerkin finite element method for elliptic partial differential equations. Dr. Naresh Kumar, it is over to you.
Thank you, Dr. Sivaras, for such a nice introductions. So today I just discussed about the weak Lurkin methods. So for the easy understanding, I just opt a simple elliptic problems, and then we will see like how to apply the WG method on this elliptic PD. So I just this is my research like this talk plan is we start from the motivation and then we discuss like about the what is the WG method, and then I also discuss the computation part for a simple problem, and then we will see the error analysis using the WG method. So in the numerical analysis, basically there are some sorry
Yes, sir.
for
Yes, sir. No problem, sir.
yeah.
No
So
problem,
I
sir.
just lost the connection.
Yes, sir.
So
Yes.
yes, yeah. So this is the problem. Like, can we solve this L of U is equal to F? So it's sometimes it's very difficult to find the analytical solutions for this equation one. So can we search any other methods to find the solutions? So we have the numerical approach. So basically, if we apply some numerical approach, then we have to first we have to reduce our in finite dimensional space into finite dimensional setting due to the implementation part. So first we restrict our space x and y to xh and yh. That is the finite dimensional space, and then we construct another operator that is LH. Instead of L, we construct an LH, and then we are looking that operator should be invertible. Then we are looking a solutions of LH UH equal to FH. So now we are looking UH instead of U. We are looking UH, and here H is like the mesh size for the any given domain, given discretization domain. So now we are looking UH instead of U. So UH we called it UH is our approximate solutions instead of U is the analytical solution and UH is approximate solutions. But if we find the approximate solutions, then there will be some error also. So now we have to measure the error in some norm. That could be any norm. So the next part is like if once we find the solution UH, then we find then we measure the error also. And then there are some types of error, like one is the suppose UH is approximate solutions, and then on the discrete grid points, when we calculate the analytical solutions, then we called it is capital U, then we measure the error. And once we apply this any numerical scheme, then we also find the consistency error. Basically the consistency error measure like how nearly the true solution satisfy the discrete equations. Discrete equations means L of U is equal to F is the equation in continuous setting. But when we solve this equation in discrete setting, then we called it the discrete equation. And if this consistency error goes to 0, then we called it our scheme is consistent. And then we also discussed the stability part in the most of the numerical scheme. So if our operator LH inverse is bounded, then we called it is the our scheme is stable. And then using the stability and the consistency, we can actually find the error estimate. So if our error can be bound by the stability constant and consistency error. So this is just a brief overview about the numerical analysis. In any numerical scheme, you can apply finite difference, finite element, finite volume. So basically these are the basic fundamental tools in every numerical scheme. So these steps we have to clear all these steps, and we have to measure the error and the stability and the consistency. Now I just give a brief overview about the simple model problems. Like this is the Poisson equation minus Laplace in u is equal to f, and we are taking just a homogeneous boundary. So the first, I hope you know about the weak formulations. So basically, if suppose u f is only square integrable, then we cannot find out the classical solution, because for the classical solution we need C2 function. But if f is in L2, then we cannot obtain C2 function. C2 solution solution C2 space. So that's why we have to apply the weak variational formulation approach. So for the variational formulations, we are just define a bilinear map, and then we say we are looking a solution U in capital V. That could be any Hilbert space, and then it may be a Banach space also. So we are looking a solution U in capital V for this AU or A of UV is equal to LV problem. So here for this problem, A of UV is the grade U grade V, and L of V is the right hand side. This is F of V, and this bracket notation is just a inner product in L2 on L2. L2 means the square integrable functions. Then this is the classical, this is the continuous approach, because here U belongs to capital V, that is the infinite dimensional space. Then if we apply the numerical, if we think about the fundamental tools in the numerical analysis, then this is the continuous setting. Then if we want to apply some numerical scheme, then we have to discretize the domain, discretize the space, and then we discretize the operators also. So here we are taking VH is a finite dimensional space, AH is a bilinear map, that is A is bilinear map in continuous setting and AH is a bilinear map in discrete setting. And IH, we sometimes we use some interpolations also, because for the some types of problems it's difficult to find the direct error, like the error between exact solution and the true solutions and the approximate solutions. So we use any intermediate operators. So sometimes we use the interpolations that could be helpful in the error estimates part. And then we define a scheme. Suppose we cook the bilinear map, the finite dimensional space, and the interpolations. Then we can define the numerical scheme. Then the numerical scheme say we are looking UH instead of U. But if we are looking US, then the solution should be in some space, discrete space, that is the VH, and then it should satisfy this equation P star. So this actually this is the approach from the variational. Suppose we have a variational formulations, and then how can we define the scheme? So here up to now we are just say like in any numerical methods, like finite element, in any finite element methods, because there are lots of finite element methods have been developed, like DG methods, various DG methods, WG method, HHO methods, so finite volume methods also. So here this is just a general approach. Now one in the finite element method, the one interesting point is like first we have to discretize the domain. So if we apply the finite element partitions for the domain omega bar, then we are taking any triangulations or rectangulations for the partition of the domain, and then we define the base parameter. So when you discretize the domain using the, suppose we are taking the triangulation or triangular, then the largest side of the triangular is called the diameter of the element, the HK, and when you take the maximum of all the HK, then you can define the base parameter H. And then using the element, when we discretize the domain, using the element, suppose K is the element, then on the each element, we restrict our functions by some polynomials. Then we define the we have to take taken any polynomial space also, and then tau h is the collection of all the functions. So we called it, it is a tuple k, pk, and tau h. So k is element, and when you restrict a function on k, then you have to use some polynomial space. So we are using the pk polynomial space, and tau h is the collections. So the finite element method actually gives a minimal discretization error, because if this is a suppose this is a domain, then if you apply finite difference scheme, then here you can easily see like the discretization error is large. But if you apply the triangulation instead of the finite difference, then it's the error is very small. So basically it helps you to in the discretization part, if we apply the finite element method instead of finite difference grids. Now I just briefly explain. You already covered this topic like in the finite element method. So in the finite element method, like classical finite element method, basically you construct the space VH, but there is a restriction, like your space function should be continuous, and where you restrict on element, then it belongs to some polynomial space PK, and then first you can work on local space for each. First you can work on each element k, and then you can assemble all the elements. So this is for our last model problem, elliptic PD. And then the consistency part is in finite element method. Actually, if you uh, take the classical finite element methods, so consistency follow by default, because in the classical finite element method we assume that our finite dimensional space VH is a subspace of the continuous space V. So if we impose these conditions, then consistency automatically follow, and we called it, it is a Galerkin orthogonality. So this property is very important in the classical finite element method, because it helps you in the error analysis part. It helps to reduce the complexity in the error analysis. So this Galerkin orthogonality is the key point in the classical finite element method. And then using these properties, like some polynomial interpolations, approximations property, Galerkin orthogonality property, then we can derive these estimates in L2 norm and in H1 norm, or sometimes we called it the gradient norm. So in L2 norm, we have obtained k plus 1 order of convergence, and in the gradient norm or H1 norm, because both are equivalent, so we can get k order of k. So here in L2 we obtained one order higher. So our objective is like how to analyze these error estimates under different circumstances and different assumptions. So here I am discussing some challenges in the classical finite element method. Like in the classical finite element method, one challenge is like discretization, because they allow only triangular or tetrahedron in 3D, triangular or rectangular in 2D. So if you want to apply some other discretization approach, then they don't allow. So basically, suppose if we hybrid maze or maze with hanging nodes are not allowed in the classical finite element method. So these are mazes where, suppose in the first maze we are using the Bernoulli or polygonal mazes. This is not allowed in classical FEM. And this is the hybrid maze, like one is the polygon and one is the triangulations. So this is also not allowed. Non-convex, this is the non-convex domain. So mesh, this is also not allowed. And this is the example of the hanging nodes. Hanging node means when like the other two, when the say range is uh, discretized by some by intermediate vertices by other elements, then we call it a hanging node. So due to this, the other one is like suppose if VH is not a subspace of V, then this equation as UVS is equal to FVS may not hold. And due to then maybe we may face a problem of consistency. So due to this, the Galerkin orthogonal property does not hold. So this is also a main restrictions in the classical finite element method. And another one is the continuity, like your function space. When you define VH, then our function should be continuous. So that is also one of the restrictions. And in the higher order basis functions, like because in the classical FEM we used the Lagrange basis functions, so it's sometimes it's difficult to use the Lagrange basis functions for higher order to construct the basis function. Now I just pose a simple question, like suppose we have a linear polynomial, piecewise linear polynomial for in the two dimensional. So it's the general form of the first order linear polynomial is a plus bx plus cy. And if you use this rectangular maze, then here you can see in the rectangular maze we have four vertices, but here we have 3 degrees of freedom, only a, b, and c. So if you use this polynomial in the rectangular maze, then the one vertices is always free, and that may cause a problems in the continuity. So we have to for this type of functions on the rectangular maze, we have to use the discontinuous approximation like this. But suppose if we use the discontinuous approximations, then there is a problem, like when you join two elements, then there is a jump. So you have to handle that condition also. So now we look into this matter, like how can we overcome these challenges that was in the classical FEM. So in the literature, like various methods have been developed for the discontinuous functions on polygonal basis. So the method, like these type of method may be easy to construct. Higher in these methods we can easily construct higher order elements, and flexibility in the mesh generation also, like we can use polygon mesh, non-convex mesh, or hybrid mesh also, and mesh with hanging nodes they are we can take. But in the DG method actually have some problems, like they use when they use the polygonal meshes, so they actually there are some large global degree of freedoms in the system of equations. So that is actually the computational cost will be very high for instead of the classical finite element methods. So now can we, if we take the same base and same polynomial of degree, then in the instead of D3, the classical FEM will be better. But for the polygonal basis, classical FEM is not applicable. So that's why we have to use some DZ approaches. Now the challenge is, like, can we minimize these disadvantages? Like, can we develop a method like other DG type of method that could be the computational cost may be decreased, or maybe some error analysis part also like can be reduce the complexity in the computation part and in the error analysis part. So recently in 2013, this Galerkin methods developed by Professor Junping Wong. So they actually developed first they developed the Galerkin methods for elliptic problems, for second order elliptic problems, and then they also apply the develop the mixed Galerkin method also. So in 2014, so this method is not like old methods. Recently they have developed, and then people also use this theory in elliptic for the parabolic PD and hyperbolic PDs. So these are some main characteristics of the WGFEM. Basically, in the WGFEM, we use the hybrid unknowns. Because hybrid unknown means, suppose we have this maze. Okay, this is a pentagon. So if we use this maze, then here you can clearly see there are 5 edges and one is the interior part. So in the WG method, we split the function into two parts. One is for interior part and one is for boundary part. So we called it face or edge, and interior parts we called it is a cell or elements. And then we define the V gradient operator, and we have to add, because it's a discontinuous method, so we have to add a stabilizer term also to maintain the stability and the coercivity. And this method is actually, if we apply these methods, then we can obtain the higher order convergence. So this is the basic feature of the WG method. So basically, suppose K is any polygonal or polyhedral domain. So first I already discussed, like this is if this is a mesh, then in the WG method we used hybrid unknowns. One is for interior and one is for boundary. So here you can see, like suppose K is a polygonal domain, then we split the function V into two parts, V naught and VP. So we called it is a weak functions. Both are integrable, but for the interior we called it is a V naught, and for the boundary we called it, or for the edge we called it is a VP. And when we take the collections of all these functions, we called it is a weak function space. But still it is, because V naught is L2 square integrable in interior, and VB is the square integrable functions on the boundary or on the edges. So still this is a infinite dimensional space. Then our target is, how can we define the finite dimensional space in the Galerkin method. So we first we have to define the degree of freedoms for the finite dimensional space. So suppose we have this maze. This is a combination of the maze. Suppose this is a triangle and these are polygon. So for the maze, we have to define the degree of freedom. So here you can see, clearly see, like we have two uh, functions separately. One is for interior and one is for boundary. Then we have to define the degree of freedom also inside the domain, inside the mesh, and on the edges separately. So here the red dot denotes the degree of freedoms on the edges, and this green dots actually this green dots actually represents the degree of freedom inside the elements. So suppose if you take k equal to 0, then we only the constant polynomial. So we need only 1 degree of freedom for edge and 1 degree of freedom on face inside the element. And if you take k equal to 1, like if you take linear polynomial, then inside the element in the two dimensionals, we need a plus bx plus cy, general form of the linear polynomial. Then we need 3 degree of freedom. And on the edge, because edge in 1D, so we need only 2 degree of freedom. And similarly for K2. So we can define the degree of freedom in this way. And then we define, we add a stabilization part to weakly enforce the matching of elements. So basically, here you can clearly see, like inside the element, we are taking different function, and for the edges part, we are taking the different functions. So we have two different functions. Then how can we minimize the discontinuity between them? So for that part, we have to add a stabilizer term that can handle this discontinuity, the jump of this discontinuity between the interior part and for the edges part. And then we assemble, first we work on the local element, and then we assemble and find a global solution. Now we define the finite dimensional space, because here this Vk is a infinite dimensional space, just a collection of weak functions. And then we already define the degree of freedoms. Then we define the Galerkin space. So it's a in short, I called it is a WG space. So basically, it's a collection of all the functions which are in pair, like V naught and VB. But when we restrict V on the interior part, then it is approximate by polynomial of degree K. But when you restrict the function V on edges, it is called the VB. That should be approximate by some polynomial of degree J. But here you can note that, like we are taking pk in the interior and pj in the on the edges. So like there is no relation, like you can choose k is different, j is different. You suppose k equal to 1 and j equal to 0 or j equal to 2, you can take any number, positive number. And then if this is a function defined, this is a we called it is a local WG space because we define on element k. And when you assemble all the local space, then you called it's a global space VH. So this is the notation for global space, and VH on K is a local space. And now we define, because in the if we take the Poisson equations, then our weak formulation is grade U grade V. So here we have to define the gradient operator also in the V-Galerkin setting. So we called it is a V gradient operator. So V gradient operator is defined from the local space to polynomial of degree L, because gradient is a vector valued function. So we are taking PLK cross PLK in two dimensional. So you can take D also, D is the dimension. So the idea basically to define the V gradient, the idea comes from the integration by parts. So if you take the classical integration by parts like grade U into K, so this is basically the notation for integration. So when we apply the classical integration by parts in this way, then here you can see like U, and here on the boundary also U. But we split the U into two parts, U naught and UB. So we are taking, instead of U, in the interior we take U naught K, and on the boundary we take UBK. So that's the difference. So here the gradient is replaced by V gradient. So this is called the V gradient for any Q belongs to polynomial vector valued polynomial space. So this is the key point in the WG method. So we have to define the V gradient operator in discrete setting. And another key point is this one. The static condensation part is very, very important in the computation part because it reduces the computational cost. So basically, we define the degree of freedom like this way. So suppose you can imagine, suppose we have a square, then we split the square into first we split into four parts, and then again we take the refinement, and then we split the interior square into four parts. So first we take uh, we work on the local space, like on the each square. First we work on the each square. So here the three dots interior side called, like we are taking P1 polynomial, and on the two red dot denotes we are taking the P1 polynomial also on the edges. And then when you first you work on the local, and when you assemble all the elements like this, then we called it is a assembly process in finite element method. And then after that you apply the static condensation. Static condensation means we remove the interior degree of freedoms, and we work only on the uh, face or edge degree of freedoms. So here you can see that like we are only red dots. So this process, using the static condensation process, we can first we just remove the interior degree of freedoms, and first we will work only on face degree of freedom or edge degree of freedom. And here you can see that like red dots are lesser than the interior dots. So now we work on the red face degree of freedoms, and then once we compute the UHB, then we using the UHB, like the face degree of freedoms, we can calculate the cell degree or interior degree of freedoms. So it's reduced through this process, like it's reduced the computational cost. So this is helpful in the computational part basically. Now we have to define because we already defined if you like go step by step, then the first step is discretize the domain that we already we have already taken that polygon discretization, and then we define the finite dimension space VH local and global. And now we have to define the bilinear map on each element. So we called it AK is our bilinear map, that is from VK cross VK to R. Here VK is a like local WG space. So if you take the Poisson equation, then basically the AK is the V gradient U naught, V gradient W naught. And we add a stabilization part also. So stabilization part helps you to minimize this discontinuity between U naught and UB. Basically, U naught is a different function and UB is a different function, but somehow can we manage the discontinuity between them? So our target is like we are adding the stabilization term in such a way like U naught, and when we take the difference between U naught and UB in some norm, then that should be less than some tolerance. So it's approximately goes to zero. Then we for that we define the stabilization part is this way on edges. So this SK is a stabilization part. Now everything is ready for ready to apply this WG method for simple elliptic problems. So here you can see like we already defined the Galerkin space, and we discretize the operators like bilinear map. Then we can easily define the WG method on elliptic PD. So suppose this is a Laplace equation, Poisson equation minus Laplace in U equal to F. So in the continuous setting, it's the continuous setting, we are looking at solution U in H01, and then it satisfies the equation 3. And we already know like in the continuous setting we have a famous theorem, that is the Lax-Milgram lemma, and using this we can easily prove the well-postness of this problem 3 in the continuous setting. Now here you can see we are taking U equal to 0 on boundary, so it's a Dirichlet boundary conditions. So if you apply the Dirichlet boundary condition on WG space, so VH, we take the notation VH0. So VH0 means we are taking the function in VH, but VB here, notice that V naught is responsible for interior part and VB responsible for boundary part. So if you take U equal to 0 on boundary, so when you impose this condition on WG space, then VB equal to 0 on boundary instead of VH is equal to 0 on boundary. Okay, if suppose the same thing if we apply in classical finite element method, then here we can write VH in capital VH and VH is equal to 0. But here VH has two components, V naught and VB. So we cannot take VH here. So we are taking VB equal to 0 because VB is only responsible for boundary part or edge part. And then we can define the bilinear map. So now we are looking a solution UH in this VH0 space, that is a finite dimensional space, 0 on boundary. And then we are solving this equation AH is equal to FVH, and for all VH belongs to VH0. So now this is the Galerkin algorithm, like in this this is the discrete setting, and now we are looking UH instead of U. So now we define same thing like previously I defined the tuples in the finite element method, that is the K, Pk, and the last one is the collection of all the element tau s. So in the Galerkin's method, I already discussed like we are taking hybrid elements, interior and boundary, and one is we have taken the discrete V gradient operator. So we need three polynomial spaces. One is for when we approximate the interior parts, so we require one space, polynomial space, we approximate by some polynomial, and for the edges part also we approximate by some other polynomial, and for the gradient part also we approximate by some other polynomial. So here I am taking Pk for the interior part, Pj for the boundary part, and for Pl is for gradient part. Okay, so here we are taking Kj and L, but here I tell you like there is no relation between Kj and L. Like you can take any degree for interior part and for boundary part and for the gradient part. But in the literature, we have in my PhD work, I have developed a systematic study for the WG method. Basically, the question was like, how can we select K, J, and L? Suppose someone can ask you, like how can we choose the degrees of polynomials like K, J, and L? So for that part, in the mathematical study, I have developed the error analysis, like what type of combination you can take for the optimal order of convergence. So the best combination was you can take the same degree for the interior and the boundary, and 1 degree less for the gradients, like pk and pk minus 1, or you can take kk and kk minus 1 k minus 1. So two, three combination you can take, but if you take the random combinations, then basically in the computation part you can do, but in the implementation for the theoretical purpose, you cannot obtain the optimal results. So that is not useful. So for that purpose, we just take three types. Mostly we take two types of combination: k and k minus 1, or k minus 1 or k minus 1. So for examples, P1, P naught, P naught. Or you can take also P1, P1 and P naught. So now I just briefly explain about the continuous finite element method or classical finite element method. Like this is the discrete setting, like a U S V equal to FV, and then you define the classical finite element method. We define the Vs by spain by some basis function phi 1, phi 1, phi 2, phi n, and then we say like UH is in Vs, then UH can be written as a linear combination of basis function, and when you put UH in this equation 5, then we get a system, and ultimately here A is the invertible matrix, then we can obtain the coefficient C. Okay, so basically this is the idea from the classical finite element method. Now I will explain you like the same thing can be applied in the WG method, like how can we implement the WG method for the elliptic, suppose for simple Poisson equation. So now in these sections, I will discuss the computation part. So suppose for the uh, easy way, I just take the linear polynomial in the interior part and the constant polynomial on the edges. So this I just calculate this WG element in the 2-dimensional. So here I just take, for the easy purpose, I just take 2 elements. Then we can, if you see, if you do the computation in 1 element, then the same process will follow. So you don't need to do the computation for each element separately. So if you can just do the computation for 1 element, and the similar idea will follow for the other elements, and then we assemble all the elements. So for the easy purpose, just I take the square, suppose unit square 0, 1 cross 0, 1, and then I just split into two parts, T1 and T2. So here the first idea, suppose you are blank, you don't know like how to apply the WG method for this simple domain. So basically first you can think step by step. So first we have to define the WG space. Okay, so we define the WG space in this way: VH is the collection of all the pairs V naught and VB. So here I already told you we are taking just P1 polynomial and P naught polynomial. So here when you restrict your V naught on element, then it is approximated by P1, and when you restrict on edges, then it is approximated by constant polynomial. And because we are taking the homogeneous boundary, so here I define VB is equal to 0 on boundary. So this is our VH space. Okay, then it is a finite it is a finite dimensional space. So definitely, if you think about the classical finite element method, then VH should be spanned by some basis function. So here the same idea we are applying. So here you can see in the interior, it is a 3 degree of freedom. So we have to choose 3 basis function. So 3 basis function for T1 and 3 basis function for T2. So total 6 basis function we require for both element, and they are sharing one edge. So we have to define one basis function for edge also. So total basis function is 7. And here on boundary, this is 0. So we don't require to define the basis function for boundary part. Okay. So here VH is a spanning VH can be spanned by basis function phi 1, phi 2, phi 7. And tau h is the collection union of two elements. Like here is just a notation mistake, like it's a T1 union T2. And here, that is the interesting point, is like you have to notice phi I. So suppose phi 1 is by phi 1 have two components, phi naught and phi b. Phi naught for interior and phi b for boundary. So now we define the basis function. How can we construct the basis function? So in the classical finite element method, when we construct the basis function, we use the Lagrange interpolations. Okay, so we called it the Lagrange basis function. But here we define the simple basis function. Like we just take, suppose we have P1 polynomial. Then what is that basis function for P1? From the linear algebra, we can easily construct the basis function like it's a canonical basis function like 1x and y. So we just define the basis function in that way. So it can be easily defined for higher order also. So suppose if you take P4 element, then you can easily define how can using the canonical basis, you can easily define the basis function for higher order. So that's the easy good point in the WG method. Like we can easily define the basis functions for the higher order also. So now if you define phi 1, so phi 1 is we are taking 1 on interior but 0 on 0 otherwise. So basically for the other parts it is 0, and phi 2 is x and phi 3 is y, and 0 otherwise for the particular T1. Okay, and similarly for T2 we define phi 4, phi 5 and phi 6, and for the edges we define, because on the edges we are taking constant polynomial, so we define uh, 1 on edge and 0 otherwise. So these basis functions we set. Now the next part is, if we settle the basis functions, then we have to find complete gradient operator, because in the bilinear map we have v gradient of u, v gradient of v. So now we calculate the v gradient on basis function. And if you calculate on basis functions, then us can be written as a linear combination basis functions. So basically then you can compute v gradient of uh also. So first we calculate the v gradient on basis function. So first we recall the definition of the v gradient. We say on v gradient of v into q, this is a notation of L2 integrable function. This is the operators the change integration by parts. It's just an integration by parts. The only change is here you have v naught and here you have to take vb. The only difference. The rest are like just a integration by, and here q is a function. Q is a function from the vector valued space p naught cross p naught. Now p naught cross p naught can be spanned by this canonical basis function, that is 1, 0, and 1. So if this p naught space is spanning by 1, 0, and 0, 1, then here you can see v gradient is a v gradient belongs to p naught cross p naught. And if p naught cross p naught is spanned by this, then we can write this one, c1 1, 0 plus c2 0, 1. So we can write v gradient is a member of this space. Then we can write a linear combination from the basis functions. Okay, so this is simple linear algebra. And now assume we are calculating phi 1. Suppose we start from phi 1. So what is the v gradient of phi 1? Because v gradient of phi 1 is just a linear combination of 0 and 0, 1. Now in the definition you can set, because we are calculating phi 1. So here in the v1 you can set phi 1. So here just see the definition. V gradient phi 1 comma q is equal to this v naught. It's a phi naught grade dot q and phi b q dot n. Here n is the unit normal, outward normal vector. So now put the definition, put first replace this v gradient phi 1 by this c1 10 plus c2 01. So here you can replace. And then phi naught, phi 1 naught is what? So here you can say phi 1 naught is this one, 1 on interior. So here for the interior part, we are taking 1, and q grade dot q is constant. Here you can see q is either, you can first you take q is 1 0. So what is the divergence of 1 0? It's 0. So here you can take 0. Divergence here, phi naught is 1 and divergence of q is 0. So you take 0, and then phi b is 0 because phi 1 is responsible for interior and otherwise 0. So what is phi b? Phi b is 0 and q is 1 0 and dot n is equal to 0. So this is the 1 0, 1 into 0 0 0 into this 0. So the output is 0. And similarly, for if you take q equal to 0 1, so first compute this V gradient of phi 1 can be written as C1 this one plus C2 this one into Q is what? Q is 0 1. So this, when you solve it, then you may get this one, C1 phi 1 0 plus C2 0 1. And then again put phi naught is 1 and grade of divergence of Q is 0. So this is 0. And again, this just replace 1 0 by 0 1. But again, output is 0. So basically, if this combination C1 plus C2 is equal to 0, C1 this plus C2 this is equal to 0, when you solve the system, basically you will get C1 is 0 and C2 is 0. So hence, if C1 and C2 are 0, then what is grade phi? Grade phi 1 is C1 into this one plus C2 into this vector. But C1 and C2 are 0, so basically gradient of phi V gradient of phi 1 is 0. Okay, so here we find our V gradient of phi 1 is 0 on both the element K1 and K2. Similar process you can apply for K2 also. So similarly, these ideas, if you apply for phi 1, phi 2, phi 3, phi 4, phi 6, up to 6, you will get the same answer, the 0, due to this thing. The divergence of Q is 0. So, and phi B, first component kill due to this, and the second component kill due to phi B, because once you define the basis functions in the interior, then it is just a construction of this basis function in such a way it it will be automatically 0 on the boundary. So that's why this part, when you calculate the gradient and inside the element, then this part is always 0 because of the basis function. And if you take the constant polynomial for the gradient operator, then this part will also 0. So every time if you take constant and polynomial, then you will get in the inside the element, the gradient of every basis function will be 0. Now one basis function is left, that is phi 7. And now we will discuss like how can we calculate the grade phi 7. So V gradient of phi 7 is what? It's just a linear combination of 1 0 and 0 1. The same idea we will apply. So up to now here you can see the change. In the first part, this this was 0. For phi 1 to phi 6, this was 0. But now this one is 0 because phi 7 is responsible for edge. So it's not responsible for interior part. So if you take phi 7 is a basis function, so basically on the interior part it is 0. So this component will be 0. Now here we take phi 7b, that is the responsible for edge part, and 1 0 dot n. But here if you solve this one, this is just a integration. So if you solve this integration, so this is a constant and this one is 1. You can like we define the phi 7 in such a way, it is 0 1 on edge and 0 elsewhere. So phi 7 is 1, phi 7b is 1 on edge. So this is 1 and this is 1 0 dot n. N is outward normal vector. So we can split n is n1 n2, both though two component n1 n2. So basically 1 0 dot n1 n2 is n1. So from here you get n1. But when you take the integration, so what is the, when you take the integration on edge, the integration of constant function on edge is what? The length of edge. So we get the length, this mod e is the length of edge into n1. N1 on, this is just a notation like n1 on first element k1. Now instead of 1 0, if you take q is equal to 0 1, then now it is n1 n2, so n1 is 0, so you will get n2. So length of edge into n2. So when you solve this, basically c1 and c2, because from this side you will get the area of the triangle. So for k1, so from the you get this coefficient c1 is the length of edge divided by area of element into n1, and c2 is the length of edge divided by the area of triangle and element or into n2. Then if you have c2, then put into this equation c1 into 1 0 plus c2 into 0 1, then basically you will get mod length e into divided by area into n. N is just a combination of n1 and n2. And on k1 and on k2, just change the constant are same, like length of edge and area of k2 into the unit normal on k2. So this is grade 5-7. But we are computing grade 5-7 into grade 5-7. Then what is the result? So basically, these are the summary, like V gradient operator for 5-1 to 5-6, it is 0. That we already calculated. And the last vector basis functions was 5-7. So if you calculate V gradient of 5-7, then you obtained length of edge divided by the area into unit normal vector for k. But we are taking k towards the collection is only two element, k1 union k2. And now this basis function you can put into the original equations. So basically the grade 5-7 into grade 5-7 is what? The when you assemble, because first you work on k1, then you work on k2, and assemble means when you take the V gradient 5-7, V gradient 5-7 on K1 union K2, then basically it is a K1 V gradient on K1 plus V gradient on K2. But we know V gradient on K1 is thus more, this is more area length into divided by area. But so when you multiply both the elements, so it's length square edge mod e square divided by mod k square. But when you take the this is the constant number, so that is you can take outside. But when you take the integration, so again you will get a area. So that's why in the like the denominator we only get mod k, but in the numerator we get mod e square. So we get mod e square by mod k1 plus mod e square by mod k2. So this is the computation for V gradient. And then this we can implement in the MATLAB also. Like simply just we have a number, so we can store like this one, and then we can obtain the output. And now I just briefly explain some analysis part also. But to for the analysis part, basically we have to define some norm also for the Galerkin space, because we define the Galerkin space VH, then we have to define for the Galerkin on the Galerkin space we will define that norm. So one norm is automatically generated from the bilinear map. We called it as a energy norm. So this AK is our bilinear map. So this can be, we can easily prove that this triple bar norm is called the energy norm. It is associated with the bilinear map. And one, sometimes it is like not possible to express the bound a priori bounds in only single norm. So that's why we need some other norms also. So for that purpose, we define a new semi-norm also, that is associated with comes from the this parts come from the bilinear part, and this part come from the stabilizer term. So this is also a this we define this notation for semi-norm. So we two norms define on the space VK. Okay, VK is what? A VK is a global local Galerkin space. Okay, and then we can prove that these two norms are equivalent. Equivalent means like triple bar norm is also less than is less than equal to this norm, and this norm is less than equal to this norm. And then This is discrete stability part is very important in the WG method because it helps you to prove the well-postness of the model problem of the discrete model problem. So this is the discrete stability, like AK is great. AK follow the coercivity and also follow the boundedness. So it's like the responsible for the well-postness of the discrete problem. And now these we also in the analysis we use these some important results that are very important in the WG method. One is the trace inequality, or even it's not in WG, even in any polygonal method like in virtual element method or in hybrid higher order method. So these trace inequality, inverse inequality, and Poincare inequalities are very important to derive the convergence analysis path. So this trace inequality, say, like briefly I can explain, like it's responsible. Suppose if phi is in H1K, then the norm on edge can be replaced by norm on element. Like the question is simple, like roughly we can say it actually helps you to convert your edge norm or the boundary norm into the interior norm. So here you can see the phi defined on the norm defined on edge that can be less than equal to phi on interior and phi grade phi on in interior. So, but we have to manage this part. We multiply by HK here and HK inverse here. So there is the derivation for the trace inequality in any standard book you can see. And this inverse inequality is also very important. Inverse inequality say how can you come from the gradient norm to the L2 norm. So if you come, if you want to come uh, from gradient norm to L2 norm, then you have to multiply by HK inverse. And Poincare inequality say you can go from L2 norm to gradient norm. You have to multiply by some constant, and that constant depends on the domain. So these results are very important for the convergence part. And now uh, we are taking just for the convenience, I am just for this convergence analysis part, I am taking this space PK, PK, and PK minus 1. So now I hope you can easily see these you can easily understand these three notations. One is for interior, one is for boundary, and one polynomial space for gradient operator. And we have to define some projections part also, because that is useful in the error analysis parts. So I define the L2 projections. But here you can see L2 projections. We have to define L2 projections in both way. Like one is for interior part and one is for boundary part. So here I use the notation Q node. Q node is the usual L2 projections from L2K interior to polynomial, and QB is the projection on the boundary. So here we are taking, but we can combine also both the notations Q node and QB. So we say QH. So QH is the notation for L2 projections. That is the combination. It's like inbuilt, like that QH it's combination of Q naught and QP. And suppose phi is in H1K, then QH phi means Q naught phi comma QP phi. So that is the notation for L2 projection. And another, apart from this L2 projections, we define the capital I projection also, L2 projection, this notation for L2 projections on the vector valued functions L2K cross L2K to PK minus 1. So this helpful for the gradient part, and the above notation for the the L2 projection is helpful for the approximation space, approximation function UH. So now we have the approximation results that is derived in this paper. We are in mixed finite element. So in this paper, they have derived the approximation result. So, they derived that the L2 projections can be bounded by the U. Suppose U is in HK plus 1 space, Sobolev space, under some safe regularity conditions. They derived that our L2 projections follow these approximation results, and these are very, very important. So you in L2 norm and in gradient norm, both are less than equal to h to the power k plus 1. And for the pi h also, pi h projections, we have also approximation results. But there is a relation between QH and pi h. So here, when you suppose QH U is what? QH U is a function in H1, but you can, when you operate QH on U, then you can send U uh, functions into the Galerkin space. So here, if you apply QH operator on U functions, then QHU belongs to VH. VH is our Galerkin space. So if QHU is a big element of Galerkin space, then we can operate the V gradient. So when you take the V gradient on QHU, then with the test function tau, that is belongs to pk minus 1, then this is the definition of the V gradient. So QH split into Q naught and QB. Then here you can apply the definition of L2 projection. Q naught U is nothing but Q naught U comma divergence of tau is nothing but U comma divergence of. This is the definition of L2 projection. And similarly, you can apply the definition of L2 projection on boundary also. And then again you apply, when you apply the integration by parts, then you get only grade U dot grade U comma tau. And grade U comma tau is just a definition of pi h projection. So when you apply the definition of pi h projection, then you will get pi h grade u dot tau. So basically, V gradient of QHU is nothing, can be equal to pi h gradient. So sometime in the analysis, you can use instead of pi h grade u, you can use V gradient QHU. And sometime you can, if you want to place V gradient, V gradient of some function of US, you can replace by pi h of V gradient of U. And now just I briefly explain some error analysis part. So basically in the error analysis part, we have a approximate solution U, suppose, and we have a suppose U is our true solution and UH is our approximate solution. So in the from the fundamental tools in the numerical analysis, we have to measure the error in with respect to some norms. So first we define what is the error in the WG method, because in the WG method we have two components of the function. So basically we have to define the error in that way. So I already discussed, like in the finite element methods, in every method the approach says like sometimes it's difficult to calculate the direct error, so we add some interpolation. So here I add the L2 projections. That is the intermediate operator. And why it's helpful? Because if you add QHU and subtract QHU, then U minus UH can be split into two parts, U minus QHU and QHU minus UH. But the approximation property helps you to bound this U minus QHU. You don't need to derive the error convergence analysis part for this first component, because that is already known by this approximation result. So this will help you to bound this U minus QHU part. So now we only care the second component, QHU minus UH. So that for that part we introduce a notation EH. So EH is nothing but UH minus QHU, and that is two component E naught and EB due to the WG algorithm. Now here you can easily understand, like in the classical FEM, the Galerkin orthogonality property holds, then we don't need the error equation. But this is the DG type method and it is non-conforming, like our finite dimensional space is not a subspace. So here the Galerkin orthogonality property does not hold. That's why we have to define the error equations. Okay, so now we take the original equations minus Laplace u is equal to f, and we test by some function v naught. Okay, but that's test by some functions from the Galerkin space. So our Galerkin space was VH0. So we test by VH0. Then here f v naught is equal to, this is the Laplacian is just the grade dot grade u and v naught, and then apply the integration by parts. Then you can reach here equation 11. But here in the equation 11, here we add minus VB naught. Here, because here you can see only V naught, but we add this part, the summation k belongs to tau h and grade u dot n comma VP. That is equal to 0, because if you suppose if you take a element like this one, then n1 and for this interior edges, for the interior edges, the outward normal for T1 is this side, and outward normal for T2 is on T1 directions, but both are same with opposite side. But when you take the summation, then they are cancelling out, and then the output is 0. So that's why you can add term here, this one. Okay, so n is the outward normal but in opposite direction, so they are same but in opposite direction. So when you sum up, then the output will be 0. So you can add this factor here, that will be helpful. And now we want to replace this part, because this is the grade u and grade v naught. So we want to replace this gradient u by some v gradient operator. Then we have to use this pi s projection. This will helpful. So if you take pi s grade u v gradient v, then you apply the definition of v gradient here. This is the test. You can treat as a finite the element of wg space, and you apply the v gradient operator on this. Then from the definition you can easily get the equation 12. This is just a you just apply the definition, and then here you will get grade v naught grade u. And now grade v naught, here also we have grade v naught grade u. So now we can replace this term by this one, plus you can take this or you can bring this term on left hand side. Then grade v naught grade u replaced by this term plus this term. Okay, so here we put, so now we combine the equation 12 and this above equation 11, then we get this one. So this equation is very, pi s grade u v gradient v. But now we already proved the result, like pi s is equivalent to the v gradient. Pi s grade u is nothing but v gradient qhu. So now here we can use that result. So pi s grade u is equal to v gradient qhu. And now this is the definition of ah. This is the definition of ah, our bilinear map. And this term is residual. Now we have to handle this term only. So here now we add a stabilization term. Stabilization part we are adding due to the minimizations of the discontinuity between the v naught and vp. Okay, so now once you add the stabilization part, then you will get equation number 14. So now in the equation number 14, we called it is a error equation. When you subtract this equation 14 from the WG approximation. What is the WG approximation? This is, suppose if we have grade f minus Laplace in u is equal to f, then what is the continuous setting? AUV is equal to FV. And what is WG setting? AHUHVH is equal to FVH. So now when you subtract this WG approximations from equation 14, then FV is common. So this is cancel out, FV naught cancel out. This is 0. And AH QHU minus UH is what? It is EH. So basically you will get AH, EHV. And these are residual. We called it L1. This term is L1 and this term is L2. L1 is this term and L2 is the stabilization term. So stabilization is what? Because here QHU, so when we find Q naught U minus QB. So now our next goal is to bound L1 and L2. That is the only target. And if you can bound the L1 and L2, then you can bound the error. And that is the convergence analysis. So it's very simple, like the analysis is not tough. Like if you here, if you apply the, first we take the L1 L1 functions here. So L1 term, L1 UV. Then first we bound this L1 term. So L1 term is nothing but V naught minus VB and this pi h operator. So you can just take the mode both side and now apply the Cauchy-Schwarz. So it's a Cauchy-Schwarz say this can be bounded by L2 norm. So you take L2 norm this one and L2 norm this one. But here you notice that both are the norms defined on only on boundary, del K and del K. Now what is the result that can help to bring the boundary norm to the interior or element norm? So now in the first step we have used the Cauchy-Schwarz inequality, but from first step to second step we are using the trace inequality, because the trace inequality helps you to bring this boundary norm to the interior norm. Okay, with some the multiply by some mesh size like HK or HK inverse. So here also, from here you in the first component you apply the trace inequality, and in the second component you can keep same, but we add the V gradient part also. So if definitely this is a positive term, so if you add a positive term, then all it will be always a greater than equal to. So now this is nothing but it is the triple bar norm, the definition of triple bar norm, because this is AK and this is stabilizer term. So AK plus stabilizer term is what? It is a bilinear definition of the triple bar norm, and this is can be handled by the approximation result. So here we apply the approximation result, and here we apply the definition. Then we obtain equation 16. So here the L1 the L1 mode is less than equal to h to the power k into u is in hk plus 1 into triple bar norm. And similarly, you can also bound the L2 term. So L2 term is the definition is this one, and again apply the Cauchy-Schwarz, again apply the trace inequality, and then you can easily get equation 17. So now we have equation 16 and 17. Then the convergence in the convergence results, just set here v you can take v is equal to eh. If you take v is equal to eh, then eh into eh comma comma is what? It is the triple bar definition of triple bar norm. So it's a eh square, and here you take L1 u eh and L1 u eh. So L1 u eh means this is less than equal to this one into eh and this one into eh. So here eh square and here eh, so you can cancel out. So eh, your triple bar norm eh is less than equal to chk in norm u in hk plus 1 omega. So here we derived a result that if u is in hk plus 1 omega, then our error in triple bar norm gives you the order of convergence of order k. And if you apply the same things in the L2 norm, then you will get the order of convergence in k plus 1. Okay, so here I just skip this L2 norm due to the time restrictions. So this is the L2 norm convergence. So here I just suggest you some important reference. This is very you can, if you want to explore more theory about the WG method, so you can go through this paper. Like this is very interesting paper. That was the initial paper of WG method, and these part for elliptic PDs, and we have developed the theory for parabolic PD and the wave equation. So we have developed the WG theory for wave equation, for general hyperbolic equations, and for the parabolic equations. So you can go through these references also. And thank you.
So thank you very much for the wonderful talk, Dr. Naresh. It is open for question and answers. Doctor, one participant is asking, sir, is the order of convergence optimal for WG method?
Yeah, because in the approximation results, we say if our solution in HK plus 1, then in L2 we have to obtain k plus 1 order of convergence, and in H1 we have to obtain k order of convergence, or H1 is equivalent to the triple bar norm. So we have already derived that in the triple bar norm we obtained the k order of convergence. So that is the optimal results in the WG method.
Any other questions from the participants?
Hello, sir. So
Hello.
thank you for the nice explanation of this method. So I have actually two queries. Like we have the triple norm.
Yes,
There
yes.
we have a term of h raised to the power minus half. So in numerical implementation, we have very small h, so that norm is going to blow or something like that. In that norm, you have h raised to the power minus half. So when h
In
going
the
to
definition,
0, yeah, in the definition of triple norm.
it's
So can
not.
you go to that
It's
definition?
it's not minus half. I think it's plus half. Uh, yes, this one. Yeah, it's a
Yeah,
square
yeah.
root.
Yeah, so in the definition of below this
Yes.
here. Yeah.
Yeah, this is the
So
semi-norm.
when
Yes.
yeah. So when we take h tending to 0, because at the end in the error estimate we are going to take that h is very small. So the this u naught k minus ubk value term that will be going to blow up.
This one, u naught minus ub.
Ye- ye- Yeah. So
Yeah. So that's the key point here. Like in the this actually this term comes from the stabilization part. Okay. So our target is
yeah.
like suppose we have two ratio like suppose a by b. Then we suppose we want to convert faster the term a with with respect to the term b. So that's why we define the stabilizers like we take in such way like u naught minus ub norm go faster than the h term. Okay, so that's like
Yeah.
this term can be dominate the your blow up part.
Okay.
So this term will go faster.
Okay, sir. Okay. Yeah, and sir, is there any disadvantage of this method? Like every method has some advantage and
Yeah,
disadvantage.
yes.
So
Basically, the main disadvantage is like if you take the suppose hexagon or for no type of mesh, then for the implementation like the computational like the implementation is like lengthy and it takes the time also in the CPU time also increase.
okay, sir. Thank you.
Convergence in the convergence part, it's like convergence you already seen like it's not tough, but for the computational purpose like this method for polygonal, if you apply this method on some hexagonal or any polygonal mesh, then sometime this it's like the computational cost is high for higher order.
Okay, sir. Thank you.
Doctor, one participant is asking, in which space VB lies if we consider an interval instead of a triangle?
Then just VB is just a number only. Suppose you take 0 1 interval, okay, and 0 1 interval you just split the 0 1 interval into four parts, suppose 0 1 by 4 1 by 2 3 by 4. So you have in the VB only you have three numbers 1 by 2 because 0 and 1 are on boundary, so you don't need to define, but you can define VB on just 1 by 2 1 by 4 1 by 2 and 1 by 3 by 4. So just a number, because in the 1D we don't have edge, we have only the grid points.
The next question is, does this method works well for hyperbolic PDE like DG method?
Yeah, in hyperbolic PD, like I just developed the WG method for hyperbolic PD during my PhD work. So you can see my papers also. So we have developed first that WG theory for wave equations, then we developed for the weakly damped wave equations, and then the general hyperbolic equations. So we have rigorously derived the results for hyperbolic problems, and the results were very, very like the computation was also very good, and we compared the results with other methods also. So you can go through my papers for hyperbolic.
Any other question from the participants? Okay. So in the absence of the questions, is there any difference in calculating the jumps? Because in this WG method, like different types of elements has been considered. They are like very complicated elements also sometimes. Is there any difficulty, Doctor?
Actually, this is the small difference between DG and the WG, because in the suppose in the DG method, like in any IPDG and any SPDG methods, in the DG methods, like the jump vary according to the problem. Suppose if you take convection diffusion equations or any some Poisson equations or heat equations, so basically the jump varies according to the problems, and then you have to add the stabilization term according to the jump. But here we fixed the jump. First we have we have added only one stabilization term, and these stabilizations will not vary according to the problem. So the jump handled by the stabilization term only. So it's don't yeah. So it's not vary according to the problem. It's just we fix the jump from using the stabilization term.
Thank you, Doctor. So any other question from the participants? Okay. So may I request the organizers to display the certificate? So on behalf of the organizing committee, we really thank you for the excellent talk on the topic, recent developments on weak Galerkin method. In your talk, you have provided a lot of information. Many participants are very much happy, and in the messages we can see that they are thanking you for the excellent presentation. The explanation about the weak Galerkin method in comparison with the classical Galerkin method, the way you have given, like for each and everything, like what is the particular difference, that is clearly explained, and it was very nice. The limitations of the classical Galerkin method and the advantages of the this weak Galerkin method, that was very well explained. The relaxation of choosing different types of elements to govern or to discretize the domains in the DG method is in the WG method is well understood. The detailed explanations pertaining to polygonal approximation in weak Galerkin space is very interesting. The information on error analysis is very useful. The explanations about the weak Galerkin mixed finite element method for second order elliptic problems are well received. So overall, we really very thankful to you for the excellent talk. And as a token of appreciation, we would like to hand over the certificate to Dr. Naresh. Thank you, sir.
Thank you. Thank you.